torque and angular acceleration. When a rigid object is subjected to a net torque, that means that the net torque is not equal to 0. The object will undergo an angular acceleration. So here is an object M, and I'm using this bamboo rod here just to show the radius that the object is moving. So if that object M is moving through that radius, and I apply a force which is perpendicular to that radius, this object will undergo an acceleration. So here I have a diagram. That's object M. I'm applying a perpendicular force, perpendicular to the radius of rotation. And this green line, just want to emphasize that that rod is considered mass-free. So we can use Newton's second law to describe this. The perpendicular force is going to be equal to mass times the acceleration, and the acceleration is going to be perpendicular, so we call that the tangential acceleration. Now, if we multiply both sides of Newton's law by r, we end up getting this equation right here. And I know, yes, the r can, of course, cancel, but what I want to do is point out the fact that the tangential acceleration is equal to the product of r times alpha, where alpha is the angular acceleration or rotational acceleration. So F times R is simply the torque that acts on the system. And mr squared, we call that the rotational inertia. So the product of mr squared, we replace that with capital letter I, and that's called rotational inertia. So rotational inertia, we also call that the moment of inertia. That describes how resistant an object is to rotational acceleration. Not constant speed, not constant tangential speed or tangential velocity, but an acceleration. So I is equal to the ratio of the torque applied and the angular acceleration. So that means that the moment of inertia is proportional to 1 over alpha. This symbol right here kind of looks like a figure 8 with the end cut off of it. That means proportional to. Don't get these two symbols mixed up. When you hand draw them, it's easy to do that. That's proportional, and that's an alpha. Now, if we backtrack and go to the equation that I wrote previously, F times R is equal to mr squared alpha, and the R, cancel one of the r's, I end up with the perpendicular force is equal to the product of mr alpha. So I want to point out the fact that the force that you apply to this object that causes it to accelerate with a rotational acceleration, that force depends on mass, that force depends on the radius, and that force depends on the magnitude of the acceleration.